In this session, let's have a good understanding of what do we really mean by clustering in the context of data. How do we do clustering? What are the different kinds of algorithms that are available for doing the clustering? In what business context will I be doing the clustering? So this is the entire thing that we are going to look at. So we'll first try to understand what clustering is all about, the goods and bads of clustering, when do we do it, when do we not do it. Then we'll move forward to try to understand when I have to do clustering, what are the various steps involved in it, right? I'm given a data and I am asked to do some kind of clustering analysis on that data. What are the most common steps that I go with? Then I'll be talking about different kinds of clustering mechanisms. So here I would like to cover 4 different types of clustering algorithms which are very highly popular. So we'll discuss about hierarchical clustering. So within the hierarchical clustering, some more time would be spent in terms of understanding how do I really assess the goodness of the hierarchical clustering model using the cophonetic correlation coefficient CPCC. And similarly, how do I really evaluate the groups that come out of hierarchical clustering? So there is a good understanding that we are going to have on hierarchical clustering. Then we'll spend some time in terms of understanding the mean based clustering, which is called as a k-means algorithm. We will also spend some time to understand the model based clustering, which is otherwise called as a M-clust algorithm, model based clustering. Then we'll also try to understand another different class of algorithms called latent class analysis, which is typically executed through POLCA kind of algorithm and a package. And once we have a good understanding of different kinds of clustering algorithms and methods, how do we really compare the various solutions that are given by the different kinds of clustering algorithms? And how do I really make a decision on which one is more and more appropriate to my data set? So this is what is the agenda for the session today. So let's get into it. The first thing, when I'm talking about clustering, I know that I'm trying to group the data. I've been given a data. I'm trying to group the data on some kind of a mechanism between the various between the various data points. I am trying to see the similarities between the various data points, and based on that I am trying to group them. So primarily when we talk about the various methods that are available, right, in one of the sessions earlier I was talking of there are hundreds of clustering algorithms that are available, and there is no way I can say that this method 1 is better than method 2 or any such kind of comparison. There is no mechanism which says for this data this method is the most appropriate one, which means the only possibility for me is have a good understanding of all the mechanisms and based on them execute all of them, see based on whatever the clusters that got created through the different algorithms, which one is more and more suitable to my business need. This is what would be the evaluation criteria. Now, coming to the different kinds of algorithms that are available. So in this session, I thought I should cover 4 different kinds of algorithms. So this is where broadly I am breaking them into 2 different headers. One is a set of algorithms which are based on distance computation. So these algorithms, they try to create groups wherein the objective is, when I am talking about the different groups like this, right? So the groups are created in such a way that the distance between the members within the group, these are the distances between these are the members within the group. the distance between the members within the group should be as much minimum as possible, should be minimized. The distance between the members within the group should be minimized, whereas the distance between the members across the groups, that should be maximized. That is the major logic behind the distance based clustering method. I want to minimize the distance between the various members within the group, and at the same time I want to maximize the distance between the members which are present in the other groups. So keeping that as the base, different kinds of algorithms have been designed. And one very highly commonly popular algorithm is called as a hierarchical clustering, which is otherwise called as H-cluster. Hierarchical clustering, which is purely based on the distances kind of a concept. So the whole set of distances are modeled in a tree structure. That's the logic that it uses. So there is a tree structure, we'll talk about it, right? We spent a good amount of time in terms of discussing this hierarchical clustering because it has a lot of advantages and applications in the real world. Then we also have another such kind of means based clustering, which is called as a k-means clustering. Instead of modeling the data in the form of a tree, it uses what is called as a group centroid. And with respect to the group centroid, the distances are typically measured. But overall, whatever is the way the distance is measured, the intention behind the distance based algorithms is they try to minimize the distance between the variables within the group while trying to maximize the distance between the variables across the groups. So those are the two algorithms that I'm going to I'm going to discuss when I'm discussing on distance based clustering methods. Then the second set of algorithms that I want to look at are model based clustering. Now here the grouping is done in such a way. So these are the groups that are formed. Now what this algorithms assume is whatever the total data that I have, they are being understood as different groups, right? Each group comes from a different distribution altogether. So the distribution of this group is different, distribution of this group is different, distribution of this group is different. When I say distribution, the mean, the standard deviation of each of the groups is going to be different. So I don't know, each of them are coming from different distributions, the data is coming from different distributions, but I don't know which data comes from which kind of a distribution. So I don't know the group membership of the data, I don't know what distribution that it is coming from, but all I know is the data that we have captured come from different distribution. So there are groups within the data, each group of data comes from a different distribution, and my objective is to understand those groups and try to segregate the data. So that is the main logic behind the model based clustering method. So I am trying to create the model such that whatever is the observed variance of the total data, I want to represent this total observed variance by a small number of groups. So each group follows a specific distribution characteristics, and the overall variance I want to express it in terms of the variance of the individual groups. So overall the group is having different mean, different standard deviation and different statistical properties. But the overall variance of the data I want to capture in terms of the variances of the small set of groups, and this is what we are calling as model based clustering method. So in short, the groups that I am identifying, they are being visualized as each group comes from a different statistical distribution. So it might be from the same distribution with different means and variances. Even then we call it as a different distribution. So all of them could be normal distributions, but each normal distribution again could have a different mean and different variance altogether. So I might very well model the things as a mixture of various distribution. Now this is where let me try to use this algorithm called mclust, which is a model based clustering algorithm, where the whole data is being looked at as a combination of different groups of normal distribution. It's a mixture of different normal distribution. That is what the mclust algorithm tries to model and identify the groups. It tries to segregate the groups based on the assumption that the overall data is actually a composition of more than one, probably two or more different kinds of groups with different statistical properties associated to each of these groups. So that is what is being done by mclust algorithm. Then moving further, POLCA, it is a latent class model. The only thing is this model purely creates a clustering based on nominal variables only. The major thing that this particular algorithm requires is it does not use any kind of scale variables for doing the grouping. It will do the grouping purely based on categorical variables itself. So these are the four different clustering algorithms that I am going to look at in the session today. But once the clusters, whatever is the method that I am using, as I said, there is no one good method which can do the bifurcation of the clusters. But what is very important for us today is once the cluster is typically created, I need to see if any of these objectives are getting met. Are there any kind of obvious differences that are present as a part of the group means? Am I able to see on some value, on some business related parameter, are there any kind of clear cut obvious differences that are present across the various clusters? And does the differentiation point to some underlying story to tell? Can I have some kind of a story which talks about where the differentiation is existing across the groups? Can I create a business case study which says on these front this cluster is different from this cluster? So when I am able to do that, that is where the real benefit of clustering is going to come up for me. Always remember, when we are doing clustering, there are two stages. First, getting a cluster solution. So to get a cluster solution, any of our four methods that I have discussed in the earlier slide, I can use either hierarchical clustering, or I can use a k-means cluster, or I can use an mclust, or I could very well use POLCA kind of algorithm, or for that matter there are so many such kind of algorithms that are there. So I need to come out with a proposed cluster solution. So these solutions will actually divide my data into few groups, and all I have to do is use those groups, see whether any business objectives are comfortably met across each of the groups. Whether I am able to establish clear-cut differences in any of the business variables across the groups, right? So that is how we are typically looking at it. Then, regarding the various steps that we get in as a part of the cluster analysis, the first step, transform the data. So in some cases, I require the data to be transformed. So different clustering methods have different requirements for the data. So probably some clustering algorithms, right, as we move we will see, let's say a k-means cluster, it uses the concept of means. So which means it definitely requires numeric data. If the data is non-numeric, I cannot use k-means clustering. Similarly, we have already talked about the POLCA algorithm. It only requires categorical data. It cannot work with numeric data at all. So I may have to transform the numeric data into categorical data or categorical to numeric in some form or the other. So that's my first step. Compute a distance matrix if needed. Some methods typically require distance matrix as the input. We'll see when we are discussing hierarchical clustering. Hierarchical clustering requires a pre-computed distance matrix, right, which talks about the similarities and the distances to each of the observation. So if at all required these kind of pre-computation before we apply our cluster, we have to really go ahead with that as one of the steps. Then choose whatever the clustering method you want to say is you want to use, and whatever the clusters and the whole clustering solution, save it as a different object so that you can compare them at a later point. And in some kind of cases, you may have to explicitly mention how many clusters you want, 3, 4, 5. So you have to rerun the cluster analysis or the clustering algorithm by changing the number of clusters. Then if required, further parse the object to obtain a solution with k groups. So sometimes do it for 3 groups, 4 groups. So you further go ahead with the object whatever you are getting and get the complete details regarding that cluster. So look at the solution, whatever the model has given with respect to the underlying data. Try to do some quick computations based on that solution. See whether you are able to find some good differences across the clusters which are more and more relevant to your business need. So these are the typical steps that we talk of in doing a cluster analysis. Before you execute any cluster analysis, I say that this particular point should be kept in your mind always. Whatever the cluster solution that I get, any of these above algorithms that I am implementing, it's just a vector of the group assignment. Okay, the first one belongs to group 1, the second customer belongs to group 4, the third customer to group 3, fourth customer to group 1. So it's a purely this kind of assignment of each customer to a particular group. But what is very much important for us is I need to have a clear-cut understanding of how do I define this group? In which aspects is this group, is one group different from the other? So I need to have clear-cut understanding of those aspects. If I'm not having, then probably there is no point in doing the clustering analysis at all. Right? Alright. So now, with this as a base, let's quickly get into performing the cluster part. Right? So let's get into the performance of the clustering using the hierarchical cluster. Now let's get started with the hierarchical clustering. It's the most popular method. Right? So we have already talked of this is a distance-based clustering algorithm. So it groups the observations based on their similarity. So the distances of the groups of the elements within the group, they should be very, very minimal. The distances of the observations across the groups, they should be maximum. So that is what is the fundamental behind the hierarchical clustering algorithm. So we would be using hclust is the name of the method which is there as a part of the base package of R itself. It computes the distances, right? It's a distance based algorithm which operates on a dissimilarity matrix. So it's nothing but when I say dissimilarity matrix, right? If I'm talking of n variables, it's an n by n matrix. So where you capture the distances between each of the pairs. So if I say 3 variables, right? If I say 3 variables for each observation 1 to 1, or if I am talking of n by n kind of stuff, I want to look at 1 to 1, what is the distance? 1 and 2, what is the distance? 1 and 3, what is the distance for the first person? Similarly, for the second person, 2 and 1, what is the distance? 2 and 2, what is the distance? So it operates on a completely dissimilarity kind of a matrix. distance between each pair of observations is typically being taken. So if I'm having a total of n data points, right, n customers, I will get an n by n matrix. So 1000 customers, I'll get 1000 by 1000 kind of a matrix. Between each pair of observation, it reports a metric for the distance. Or if I have the variables, it tries to look at based on the variables, what are the values across the customers. No, it is typically doing based on the number of customers. If there are n customers, I will get an n by n matrix which talks about the distances between each set. And the kind of method that it follows is what we call as agglomerative method. The meaning of agglomerative is this clustering algorithm works like this. If there are 1000 customers, each customer is treated as a separate cluster. So initially it starts with 1000 clusters. Then it tries to compute the distance between this and this. Each pair it has computed as a part of the distance matrix. Now based on that it will try to see which ones are the closest to each other. So based on their distances, it will try to club one at a time. So for this guy, who else is the closest in terms of distance? So if these two are the closest, these two are clubbed together. So it's a successive joining of the neighboring observations. It could be single observation clubbed or a cluster is clubbed. But until one by one is kept on joining. And this process continues until all the observations are linked. So if there are 1000, initially they start as 1000 clusters. Now each one of them can get clubbed based on the distances. So depending on the distances that are existing between the clusters, the ones which are very closer to each other, they keep getting clubbed. And that's how the whole process continues till all of them get clubbed in some form or the other. Now when I am using the word distance here, I am referring to the Euclidean distance, which is nothing but x1 minus x2 whole squared plus y1 minus y2 whole squared plus so on under the root. So if I am talking of the first person having variables x1, y1, z1, the second person's variables are x2, y2, z2. The distance between the first and the second person goes with this kind of an algorithm, with this kind of a formula, which is what we are calling as Euclidean distance. And the same Euclidean distance can very well be computed in R using the formula called dist. So I can very well use this formula dist to compute the Euclidean distance. It's only, so now let's start using this. Right, we'll try to create a hierarchical cluster. Right, that's the best way to get started. Right, let's create our hierarchical cluster. So let me take the data set first. So I'll use this particular data set, the customer segments related data set. So if I want to see what is there as a part of this, I'm quickly looking at the dim, which is saying it's a 300 rows and 7 columns, right? That is what is there as a part of this particular data set. Let me do as a part of head what is there. So it says age of the customer, gender, the income level, number of kids, right? Whether this customer has a own home or not, whether he has subscribed to something or not, and the segment of the customer. So these are the variables. And if I look at the structure, seeing what are the data types that are associated with each one, age is a numeric, right? Gender is a factor with 2 levels, female and male. Then income is also numeric. Kids is integer. Own home, subscribe and segment are looking like factors with different kinds of variables. Now, the first thing I have to compute the distance. Now, because distance is a numerical kind of stuff, I can compute them only for these 3 variables. Right? All the number variables is one where I can compute the distance. So let me first do the distance part. So let me use the variable as distance, right? Probably because it's the name of the function. Let me use it as d. Now I am using the function called distance, wherein I can take from my customer. I can't use all the columns. So I'll take only the column number, I'll take all the rows, but column wise, I'll take only the column number 1, which happens to be the age, 3, which is income, and 4, which is the kids. So I'll take these 3 columns. So based on that, I'll try to compute the distance. So I'll get the distance for all the 300 customers. If you simply try to see the dim of D, you will come to know. So the dim is actually a distance. Now this distance, I have to convert it to a matrix. If you simply see D, it gives some such kind of values, right? It is giving so much of information. So probably the best thing is convert this into, say, as dot matrix of D. Now when I do as dot matrix of D, I get the whole thing distributed in the form of a matrix. So these are my columns, right? 295, 296, 300 columns are there. Probably here I could see different other columns cropping up. So overall, right, probably if required, you say as dot matrix of D, take just 1 to 5 rows and 1 to 5 columns. So I say 1 to 5 rows comma 1 to 5 columns just to check what is coming out. A subset of it, you will see that this is the distance that is existing across. Across the diagonal, the distances are 0, right? And these are the distances. So the distance between 1 and 2 is 13,936. The distance between first customer and the third customer is 5,300. Distance between the first and the fourth is 31,000. So this is how the distances are typically coming out. The distances are very much symmetric. The distance between 1 and 2 is same as the distance between 2 and 1. And at the same time, the distance from itself is 0 because there is no distance at all. Now this is very good to use, the dist as a function, right? The dist as a function that we have computed here, it's very appropriate if my variables are numeric in nature, right? I can very well look at the matrix and I could see that it is more and more symmetric. But in our data here, more than I have more number of non-numeric categorical data compared to a numerical data. So in that case, I cannot really rely on using the distance function. Now this is where we talk about using a function called DAISY from the cluster package, which will do the similar kind of distance computation. It works with mixed data types. It works both with numeric or even the factors kind of data. So it will do a rescaling of all the values, right? There is a kind of a rescaling that is typically being done, and based on that, the results are being given. I can very well convert that result as a part of my matrix. So let me take it this way. Let me first load this package called cluster. Once this cluster package is loaded, I want to use the DAISY function. So I'll call it as DD, which is DAISY distance, right? I'm calling it as a DAISY distance using DD, or let me call it clearly itself DAISY dist, right? To have a clarity, I'm using the variable name as DAISY distance, where I'm using the function called DAISY. On here I'll give my whole cluster, what is my data? Customer. I'll give my whole customer as the input to it. Now, so it would have computed the distances across. Now what is that I can do just to test it out? I'll convert this distances into a matrix. So I'll say DAISY dist is the name of my variable. So as dot matrix daisy dis, I'll just look at the first 5 variables, first 5 distances instead of looking at the whole 300 by 300 matrix. So here I could see it has done the computation based on all the variables. Now the distance between the first customer and the second customer is 0.21. So there is some kind of a scaling that is being performed. The first, so that is what is an additional thing that is being taken care of by the daisy function. All the variables are typically scaled, right? So first and the third is the distance is 0.19, first and the fourth is 0.22, the first and fifth looks like at 0.35. One interesting thing you could see here, here the distance between 1 and 4 is 31,000, whereas 1 and 5 is 29,000. 5 is closer to 1 here. Whereas here it looks like distance between 1 and 4 is only 0.22, whereas the distance between 1 and 5 is 0.35. So the kind of distances have got changed because we have added 4 more variables as a part of this cluster solution. So we have seen these are the distances that are existing between the matrices, right? So I could say this is the distance between 1 and 2, this is the distance between 1 and 3 and so on. So we could see the distances across each of the groups. Now, once we have this distances, right? So generally we should see diagonals more or less zeros. So once this is there, I have got the whole thing as a part of my matrix. So it's better that I could have saved that information. Right, I have watched it, so I have the information daisy disk, so I can use that daisy disk as an input, and based on that I can very well run my hierarchical clustering algorithm. So I'll run my H-clust on a dissimilarity matrix. So I can very well give my H-clust algorithm now. So I'll say H. So let me call it as customer underscore H cluster, right? H cluster. So we are talking of H clustering algorithm on the cluster on the customer. So I'll use H cluster as the name of my function. My distance is daisy disk now because we have done the distance using the daisy function. And one more input that I give to this is a complete. When I say complete linkage, each and every member, the distance is being considered when it is trying to group them. So that's where I'll call method equal to complete. So that all the distances, all the customers are typically being taken into consideration. So this is how my cluster got created. My hierarchical cluster is already in place. Now this is where, if required, I can have a plot of this hierarchical cluster. Right, I'll call the plotting of customer underscore H class. So there is a hierarchical cluster that got created. So I really wanted to see what this cluster is all about. So much of clutter in the cluster. Right, I could see so many things that's happening. This is what we call as a dendrogram, a hierarchical dendrogram. Right, this is what it is. So you could see on one side there is a height, the height that talks about the relative distance between the various customers. The height is talking about the dissimilarity that is existing between the various customers. So if they are very close enough, the heights are very small. If they are much farther enough, you see the heights going much higher. So this is where all your 300 customers are, right? There is some kind of so some customers are close to each other, some customers are farther away from each other. So you could clearly see here the complete similarity versus the dissimilarity of the customers is being captured, right? So you could look at the height and where the observations are joined. These two customers are joined here itself. and these two customers are joined here. These two customers are joined here. Some customers or some clusters are joined here. So this is where we are talking about the major things that we interpret is one, the height, two, the joining points. Two major things that we interpret from this. So height is a measure of dissimilarity. So if two customers are getting joined somewhere here, so probably if you look at this particular customer versus this particular customer, they are getting joined only at this particular place, which means they are completely dissimilar in nature. So the distance, the place where they are getting joined and the height. So that's a measure of a height. So the customers who are closer to each other, they get joined at a much lesser height. The customers who are farther away from each other, they get joined at a much higher values of the height. And the horizontal branching really does not matter. Probably this group, instead of being here, it could be here. So the horizontal numbering, interchanging this one here, hardly makes any kind of a difference. So the interpretation may not change at all. But let me tell you here, it's looking too cluttered. So I may be more interested in zooming only one section of the chart. Right? Probably I may want to zoom only this particular aspect. Right? So this is where I can improvise it. The plotting, I can do a cutting of the dendrogram. So probably I may say cut it at 50%. So only this much portion will be plotted. Right? I could clearly say cut the dendrogram at a specified location. And once I cut it at a specified location, I can see only a few branches. So the way we are trying to look at it, let's say the same dendrogram, right? If I really want to use the same plot function, I will cut it into two halves. Probably let me cut it like this, 50%. And based on what I have cut, right, I can cut it into two halves. And based on what I have cut, I can look at the lower portion or even the upper portion of it. So let me just look at it. I want to do a plot this time. Right? I want to expand it, zoom it. Wherein I am looking at the cutting. Right? So first my cluster, convert this into a dendrogram object. I have a different dendrogram object. Right? I have a dendrogram object. So I'll say as dot dendrogram, wherein I am now once I have converted my cluster. What is my cluster? Customer underscore h cluster. So first customer underscore h cluster, I am converting it into a dendrogram object, and I am doing the cutting where I am setting h as 0.5. So I am taking the 50% as the cutoff, and I am cutting the h part. So, and on the top of it, I want to look at only the lower part of it. Right? I am cutting it at, let's say, 50%. So I'll cut it here. I'll observe only the lower part of it. So this is where I say dollar. So if you look at this, before doing the plot, let's look at it this way. Don't do the plot now, right? To get a clarity, just do cut and leave it. You cut the dendrogram. So you cut the hierarchical cluster that we are getting, convert it into a dendrogram object. Once it becomes a dendrogram object, cut it at h equal to 0.5. The moment you have cut it, right, the whole thing, now you have upper dendrogram with 2 branches and 8 members. This is what is there as a part of the upper. So in the upper part, right, when you have said 0.5, so there is a dendrogram object with 2 branches and 8 members altogether, because at 0.5, if you look at, this is what is going to come out, right? You cut it at 0.5. So the upper part of 0.5, this is what it is. The overall 2 branches are there. Within that 2, at the max 8 objects are there. So probably if you really want to plot that part, right? But otherwise in the lower, so in the lower you have different kinds of branches. So this is lower 1, this is lower 2, this is lower 3. Right now you can see all the different lowers that are coming up. So you could see here different kinds of lowers. So in this case you can see there are 8 lowers that are overall coming up. Let's look at the dendrogram. So there are 8 lowers that are coming up, right? This is the higher. There are 8 lowers. So whatever are the 8 branches that have come here, each of the branch is getting converted. Now this branch is converted into one lower 1. This branch is lower 2. This branch is lower 3. So if I look at the cutting at 0.5, I think 8 branches are coming up. So probably this itself will be 1 and 2. So there are 8 branches that are coming. Lower 1 is having again 2 branches, 11 members in it. The height is 0.22. Then again 2 branches, lower 2, 4 members only are there in it. But lower 3 is having 2 branches and 60 members. Lower 4 is having 2 branches and 62 members. Lower 5 2 branches and 50 members. Lower 6 2 branches and 8 members. So this is how the whole set of members have got divided. Then probably I can very well do a plotting of one of them. Right? So whatever the dendrogram that got cut, I'll do a plot. I can zoom each one of them separately. So I'll do a cut saying dollar. I will take lower, let's say 1. Right? I want to do the plotting of this one. So I'll get a different plot. Just plotting the lower 1. I'll get distances saying 261 and 293. They are very close to each other. 278 and 294 are very close to each other. Now similarly 271 and 276 are slightly away. But again these two are getting joined here. So all these are becoming, now again these whole 4 customers are getting joined with 258 here. So this is the distance between 258 and any one of these 4. Similarly here you could see 278 and 294 are very close. So I can say 278 and 294 have similar characteristics. And similarly 242 is also more or less similar to this group, slightly different from these two. Similarly 270, 283 and 288 are close enough. Again this is the distance between them. Probably I could very well say 258 and 257, they are getting joined only at this level. 258 and 257 they are getting joined only at this level, means 258 and 257 are very much farther enough. Right? Their distance is getting joined only at this height, which is a much bigger height. The same logic I can implement. Let's say check out my second cut. This is what is my second cut. 84 and 95 are together. 20 and 53 are together, but these two are getting joined here only. Similar. Now you can go ahead and visualize each of your cuts. So 3 is looking much bigger because we said they had 60 members. So you can do the cutting wherever you want. This is primarily to zoom up. My overall dendrogram might be looking quite heavy, so I can very well make a cut, and based on that I can have a kind of close lookout each of the branches, right, so that I can get much detail. Even here I could see with this much of cutting, again a few groups cannot be observed that clearly, right? So now if I really want to observe, right, just to quickly check out. So in this I've seen that 261 and 293 are pretty close to each other, right? Or 278 and 294 are pretty close to each other. So let me look at their data. What is the kind of similarity they are carrying? So let me look at the customer, wherein I am taking the subset probably 278 and 294. I'll take the row numbers 278 and 294. I'll take all their columns. Just seeing. So you see age wise, they are more or less closer. Both are females. Their income is also not too different. Right? Both of them don't own any home. Both of them have one kid. Both of them have subscribed for something. Both of them belong to the same segment. You could see there's a very high similarity between the two groups. Similarly, you observe the similarities between 261 and 293. So look at 293 and 261. You could also see similar 38.5, 39.5 female. Income is also closer. Two kids, one home is yes, subscriber yes, segment is moving up. I could see lot of similarities on various variables. But at the same time, you see the distance between 258 and 257. Right? So 257 and 258, you could see they are wide apart in many aspects. Right? Let's see, 30 and 43, age is a big difference. Both are females at least. Even the income wise, there is a big difference. Kids, more or less same. But they don't, one of them is owning a house, one of them is not. So this is where the difference is clearly getting highlighted across the groups. So in the first case, we see a lot of similarities, and in the second case, we see a lot of dissimilarities coming up between the various observations. Now this is where we can use even the nearest neighbors kind of understanding. So whichever ones are very close to each other, we call them as nearest neighbors. This is one more thing where you can typically compare the various brands based on their technical specifications, etc. You can very well see which of the vehicles are pretty much closest to each other, which of them are pretty much away from each other. We can do all this kind of clear-cut understanding by looking at this cut and even exploring whatever by even exploring the stuff. You could very clearly make out by cutting the dendrogram object, by zooming it. You can very well see how each group is typically getting overall progress. I could look out for a few groups as I have done just now. I can look at the similarities and the dissimilarities that are present across the different groups. But much more than that, if I have to really evaluate the goodness of fit of my hierarchical cluster, apart from looking at the closeness, the fartherness, etc., I have what is called as a cophenetic correlation coefficient, CPCC. So this CPCC is a good measure talking about the goodness of fit of a hierarchical cluster. So it primarily assesses how well the dendrogram, whatever we are creating, whatever got created using the plot, to how much extent it is closest to the true distance metric. So we have already computed the distance between the variables. The daisy function has actually computed the distances between the actual variables. Now based on the dendrogram, we are trying to see to how much extent the dendrogram is matching the true distance metric that we have computed. And this we can easily compute using a function called cophenetic. So it gets the distances from the dendrogram and compares it to the distances that we have got through the daisy function using the correlation between them. So the output, so you can take the distances that are coming from the daisy and again the distances that are coming from the dendrogram, and you can directly use a correlation between them. So whatever the result that comes, you can interpret it on the same lines as your Pearson correlation coefficient. So if you get a very high value for CPCC, it means that your dendrogram has actually represented the distances between the customers more and more effectively itself. So this is what we can very well test by using this cophenetic function, right, wherein you can take the distances between the clusters that you have got using your daisy function, right? The distances that you have got using your daisy function and the clusters that you have created, the segments that got created using the cluster analysis, you can very well you can very well test the correlation between them by looking at the cophonetic. Take, take the cophonetic, take the cophonetic of whatever your cluster. So the cluster that we are talking of is customer underscore hclust. So this is the cluster that got created, and along with that I will compare. So I am taking the cophonetic between the cluster that I have created, right? So the cophonetic of the hclust that we have created versus the actual distance that we have got, which is called as a daisy dist. So I am taking the daisy dist as one input, customer underscore hclust as the other input, right? Cophonetic as typically is trying to get the distances. So if you look at the operation of the cophonetic here, it is getting the distances from the dendrogram. That is what it is doing. And using the correlation, I am comparing it with the daisy distance that we have got and seeing that in this case it's almost 66%. So 66% is an indication that it is more than 50%. So it's a kind of high correlation. So whatever is the way you interpret the typical correlation coefficient, you can very well use the similar mechanism even here as well. The higher is your CPCC, you can say that the hierarchical tree has represented the distances between the customers more and more effectively. So now once you have got your clusters created, the next part is just look at the groups, right? Try quickly checking out. So the dendrogram, whatever you have got, you explore the dendrogram, you can cut it into any number of into clusters at any desired height. Now this is one more aspect we have to be clear. Whatever the dendrogram that we are creating, right, I can very well cut the dendrogram when I am doing a plot of it. I can cut it at any desired height. So based on that, I'll get a different number of clusters altogether. If I want, I'll cut it at 50%, 60%, whatever it is. So based on the desired level of cutting, it can overall split the data into n number of clusters. Now this is where we simply say I can recreate my clusters, right? Or probably when I'm talking about my clustering, I use a variable called cut tree. So cut tree, CU tree, is basically where I am doing a cutting of the tree. Whatever the cluster that got created for me, I have to specify how many clusters do I need. I have to give a variable k equal to 4, k equal to 3 kind of stuff, which will tell me how many clusters do I want. So let's say here I want to look at 4 clusters, right? So this is where I really want to see number of clusters. So where I can use my cut tree. So customer underscore hclust underscore hclust n, let me use number of clusters. So I'm just using the function called cut tree. This cut tree uses one of the input is my cluster itself. So which means I'm using customer underscore hclust. So whatever the cluster that got created, on that I have to simply say how many clusters do I want, how many the whole tree, how many clusters do I want to split it into. So this I can get it in a form of a table to see the split of the customers across each of these 4 clusters. So this says my cluster 1 has 113 customers, cluster 2 has 122 of them, cluster 3 has 15 and cluster 4 has 50. So these are the clusters. So probably cluster 1 and cluster 2 are having a more number of customers compared to cluster 3 and cluster 4. Now if I really want, I can very well perform this cluster. I can really look at which customer is belonging to which particular cluster. So I can very well look at which customer belonging to which cluster, and based on that I can do my classification. So I can very well do an aggregate, right? If required, let's say I want to do my aggregate across all the variables, right? I want to do an aggregate across all the variables, and I really want to go with the cluster. So I say customer underscore h cluster n. I'll say data equal to customer, and let's say I want to compute the mean. So I get for each of the clusters 1, 2, 3, 4, right? So the average age of the first cluster is 41. The average age of the second cluster is 48, 36, 23. So it looks like the average age of the fourth cluster is much smaller. So it could be a young group of customers. Average age is looking much lesser. The average is much higher for this group. Similarly, if I look at the gender, so here it is coming out to be 1.13. So depending on what is one, if one is a female, so then this group looks like more dominated by females, whereas this looks like more dominated by males. Income level wise also, this cluster contains people who are having very less income, whereas all the other three groups are looking more or less similar with respect to income. Kids wise also, this cluster and this cluster have very few kids, whereas the third cluster is looking more heavily dominated on kids. You look at owning a home, this group cluster 2 is more of right people completely owning or not owning depending on what are the levels. Let me check what are the levels of. So if we typically look at the structure of the customer, we'll get a clarity on all these things. So you could see that no is 1, yes is 2. So because the average is 2 here, owning a home is looking like, so this group contains all owners only. The cluster 2 contains all owners, right? All owners, whereas the cluster 1 contains all non-owners. Similarly, the cluster 4 is dominated by majority of the non-owners altogether. Whereas when you look at the cluster 3, these are the guys who have subscribed to the product, subscribed yes. Whereas the group 1 and 2 looks like those who did not subscribe much, right? And similarly, you look at the gender wise also, female is 1, male is 2. So I could clearly see that group 3 is more of females. So females who have subscribed to a particular product. So you can really make out the definition of the cluster. So that's how this particular cluster is looking like, right? That is the kind of output. So you can very well evaluate the cluster more and more meaningfully just by looking at what is the kind of classification that you are getting out of the cluster. So that's how you do a summary across the clusters to see some kind of differences. Now sometimes we have to be very careful, right? Sometimes the kind of classifications that you bring out, the kind of conclusions you bring out from the clusters are in such a way that mostly obvious results are going to be brought out. So we have to be very clear, because sometimes the different machine learning techniques that we are bringing in, they try to take the path of least resistance. So in many cases, it might so happen that obvious results also come out as a part of our identification. which is actually not required to be interpreted, because there could be, here we have used the daisy function. Daisy function rescales everything to 0 and 1. So especially if I have two category functions, one would be scaled as 0, the other one would be scaled as 1. So because of its extreme values, these values will become more and more influential in our decision making process. Now this is where we have to be very clear. We can't stop with one single model. We may have to play around with multiple models, and based on that we may have to see to what extent each of the cluster solution is really fitting to our business objectives. So without doing that, we cannot really make any kind of conclusion regarding the quality of the clusters, right? And I think we can even do a plotting, right? We can do a cluster plot. Let me just see if I can do it on this data. No, it requires a numeric. So if I am doing a cluster plot where I am trying to do a plotting of the clusters, whatever the cluster that I have typically got, right? So I'll do a cluster plot. So the cluster plot that I am looking at, so I may have to look at the cluster solution. So let me look at my customer data, right? It is there as a part of the cluster itself. I'll look at my cluster data and I have to take the clusters that are coming out from this. So if I, let me see what I am getting, customer underscore h clust, if I am looking at the object. So I am getting only these things, right? Customer underscore h clust. So let me look at the structure of customer underscore h clust to understand, can I extract something more? So these are the only things that are coming out as a part of this cluster. So I have to check per h cluster n. So because it has already broken down into 4 clusters, so these are the 4 things that have come out. So only the structure wise it is showing integers 1 to 300, where it has classified each one of the customers into each of the clusters itself. And if I am simply putting customer underscore h cluster n, the output that is just giving is a series, right? It's not giving anything more than that. So if I do a cluster plot, if I do a cluster plot using cluster plot, right, let me just check. Initially I'll give the customer data, right, and to that I have to add my clusters. So let me add customer underscore h cluster n, which will give me the cluster for each one of them, and let me set the color equal to true so that I will get different colors for each of the clusters. So let me see what this graph gives. Yes, it has done an identification of the clusters. So you could clearly see the different kinds of clusters that are getting created, right? So these are the 4 different kinds of clusters that are getting created. So I require the labels also to be done so that I get a clarity. So I'll say labels equal to 4. So I say this pink one happens to be the cluster 1. The red one is cluster 2. So it looks like cluster 1 and cluster 2 are more or less superimpose. Cluster 1 is a subset of cluster 2 and cluster 3 looks like a subset of the cluster 1 and 2. The cluster 4 is looking completely different to a large extent. So that's where we have got, even as a part of our interpretation also, cluster 3 consists of a lot of young guys. So there are different variables on which the cluster 4 was more or less separated. So that's how I can very well visualize this cluster plot also. So cluster plot, where I take the data, where one data is the overall data, the second one is the cluster solution, the cluster groupings that I have. Based on that, I can go with the color and all these things, so that I can clearly make out which clusters are clearly segregated, which clusters don't have any kind of a separation between them. So that's how I can go ahead visualizing this particular cluster plot, right? So that's the typical analysis we do with respect to hierarchical clustering. Now we can move to the other forms of clustering as well to get a good understanding of the overall clustering process, right? Now, moving to the next algorithm, which is means based clustering, which is also a distances based algorithm, which we are calling as k-means. So the k-means as an algorithm, we have already discussed at the beginning of this session, that the groups that it is finding is purely in terms of distances. But how it measures the distance is, it looks at the mean sum of square deviations of each observation, not from each other. It's not x1 minus x2 kind of distance, but it creates a multivariate center. So a centroid, which is the center of each of the group. So there is a group, the center for each of the group is taken, and based on this, the value, the observation, the customers are sent into that particular group. So it is finding the group wherein it looks at sum of squares of the deviation, each observation from its centroid, which is what is the multivariate center of its assigned group. So there is a computation of the mean and the deviation of observations from the mean. So it is purely based on the Euclidean. So the main difference is there, each observation wise distances are computed, whereas here the distance is computed with respect to the center of the multivariate center of that particular group. So here most of my observations need to be a numeric data only. If they are not numeric, they have to be coerced to numeric. They have to be forcefully converted to numeric. So in this case, because almost all my variables are binary, right? Let me use all the variables. So I can very well use the numerics, right? Customer is my data. So let me call customer underscore numeric. So wherein I'll take the whole customer data. Let me not consider the last column, the seventh column. Let me not consider it, the segments. So I'll take only up to here, right? So when I look at the dim of it, I get the 6. Now within the 6, I have a few factor columns. So let me take the structure of customer underscore numeric. So these are the three factors, these are the three variables that are factors, but they are all binary. So I can very well coerce them into numeric quite comfortably. So I'll call customer underscore numeric dollar gender. I'll make it as dot, or probably let me make it as if else, because we have values. If else customer numeric $gender is equal to male I'm setting it as 0, otherwise I'm setting it as 1. And because female is 1, male is 2, I'm setting it, if it is male, let me set it as 0. If it is female, I'm setting it as 1, or it could be the other way as well. Now the same logic I can follow even for the other variables as well. Right, I'll have a renaming done for own home, where I'll do a similar process. Own home. So the answer should be here own no. So I'll set it as own no. Then it will be a value 1, otherwise it will be a value 0, otherwise it will be a value 1. Similarly, let me do the other thing also, where I set it as subscribe. So wherein now, because the requirement for k-means is everything need to be numeric, I am forcibly converting everything into a numeric form. So now if I look at the structure of customer underscore numeric, I'll see that everything is a number. Right? So once I have checked that this is numeric, this is where I can run the k-means. Now let me tell you, the k-means algorithm, right, it explicitly, so now we have the binary factors, I have coerced all of them to numeric. There is no alteration in the meaning. I have created dummy variables and I have done the recoding by using the if else. Now I am very much ready to use the k-means algorithm. But the k-means algorithm requires a seed value. So some kind of a starting point. So this starting point I can very well set, let me set the set seed as 100. So this is some starting point. Let me tell you partially the kind of solution that I am getting out of the k-mean is biased based on the seed value also, which means I have to try different kinds of random numbers, different kinds of starting points, so that I can very well compare the results across each of the processes. So now let me do customer underscore k-means. Right, I'm talking about customer underscore k-means as the name of my cluster. Right, I'm using the function called k-means, and the data that I have to use is the numerical customer data. So let me take customer underscore numeric as the input, and I have to specify how many clusters I want. So that's where I say centers equal to 4. So these are the 4 cluster centers that I am trying to create. So these are the 4 cluster centers that have come out. Now once I know these are my 4 cluster centers, I can quickly check out them. So I'll see what are those. So I could clearly see the cluster means, right? Directly I could see the cluster means here, where I could see the age of the, so when it comes to cluster 1, 2, 3, 4, cluster 3 is very young here, right? Cluster 2 is looking much older. Based on the gender, it looks like more or less there is a equal distribution across all the clusters gender wise. Income wise, it looks like cluster 2 is a very high income cluster, whereas cluster 3 is looking like a low income cluster group. Kids wise, it looks like cluster 2 does not have many kids, right? That is the cluster mean, whereas I could see cluster 3 on an average 1 kid, but cluster 1 and 4 are having more than 1 kid. And similarly, when you look at cluster 2, almost majority of them are owners, right? Whereas when it comes to the other clusters, cluster 3 looks like majority of them are non-owners. The same logics, but whereas when it comes to the subscription, it does not look anything significant. So that's the kind of grouping of the clusters that has happened. So this is what is the clustering vector. The sizes of the clusters, this is 97, this is 25, this is 63, this is 115, right? And I can very well get dollar cluster. When I do dollar cluster, I get the clustering memberships. So customer underscore K means dollar cluster. When I do, I'll get the cluster membership for each of the persons. Now this is where I can use my aggregate. Now I don't need to use my aggregate function, especially if I have to compute the mean, because I have already got the cluster means. Even if I do an aggregate function, right, wherein I am trying to look at my customer based on the customer, right, let's say all the variables dollar, so I'll put them as dot tilde. I want to group the customers. I want to get the means based on this. The data wise, I can take my customer data and I can very well talk about the mean. So I could see these are the numbers, right? It has already computed the cluster mean. So I could typically look at based on the cluster means. Only difference being here we have transformed the gender 0, 1. So here we got a different number slightly, right? Because here the numbers are 1 and 2, whereas we have transformed them as 0 and 1. So that's where we got for these categorical variables which we have forcefully converted to numeric, we got a different representation for that. And now I can very well use the cluster plot as well, just to see if there is any kind of a differentiation that I am getting with respect to the clusters. So the data wise, I can still use the customer data for my cluster plot, and the grouping, I can do the grouping based on this. So again, I can set my color equal to true. I want to set different clusters with different colors, and I want to set my labels equal to 4. I want to give the 4 labels. So this is how this clustering has come out, right? These are the customers who are exclusively a part of this cluster 3. Blue represent the cluster 3, slightly separated from cluster the other clusters. 1, 4 are looking more or less integrated. 2 is looking slightly separated. But they are not purely clearly segregated kind of clusters, but this is the kind of interaction that we are seeing between the clusters altogether. So I can visualize the clusters, right? We have checked the summary across the clusters. I have visualized the clusters using the cluster plot. So, and probably I can set the arguments like color, shades, etc., so that I can see the clear-cut differentiation between the clusters. But now here the point is there is a limitation when I am using this k-means clustering. It clearly requires I have to specify the number of clusters. Is it 1? Is it 2? I have to clearly specify the number of clusters. So if there are more than one solution, I don't have something like CPCC in case of k-means cluster. So I cannot really say which of these different clusters, like if I go with a 3 cluster solution versus a 4 cluster or a 5 cluster, I can't really make out which of these solutions is much appropriate for my kind of a data. Now this is where a limitation does come up for us, but obviously we can't go anywhere beyond that, right? So that's we have to take that as a limitation and we have to move forward. Then once we are done with the distance based clustering methods, now we are slowly moving towards the model based clustering, where we are looking at M-cluster algorithm. As we have already discussed earlier, so these algorithms make an assumption that all the data come from different groups and each of the group has a different statistical distribution. So when I am saying different statistical distribution, the means and the variances of each of the observations are completely different. So the objective of this algorithm is try to find the best combination of the groups of such underlying distribution so that you can explain the data much better. And this is executed through the mclust function from mclust package. So I have to first install my mclust package. Mclust package. And I have to use the mclust function. So this time let me call customer underscore mclust. This is the name of the clustering algorithm that I am using. So I have to use a function called mclust. Remember, m is a capital letter here. So mclust, even this works on numeric data itself, right? Because it is assuming that the data is reflecting observations from different population. So it's all talking about the data coming from different distribution. So because it's a different distribution, it needs to be numeric data itself. And mclust as a model, as an algorithm, it assumes that the data is coming from different kinds of normal distribution, which means the means and the standard deviations of each of the groups of normal distributions is different. So it assumes that all of them are coming from a normal distribution only, but the means and the standard deviations of each of the groups are different. So they are the mixture kind of distribution from where the data is typically coming from. So I can use the numeric data. So I'll call customer underscore numeric to do this mclust algorithm. Oh, I did not load. Okay, let me do a library of mclust first. Once I have done this, okay, my mclust is a kind of algorithm that is package that we are loading, and based on that we do an mclust algorithm on the data. Once we have executed the mclust algorithm, then I can do a summary of this particular algorithm, customer underscore mclust. So the way it says is, it's a finite mixture model, Gaussian, because it assumes that all data is coming from normal distribution, and there is a EM algorithm that it typically engages. So mclust EVE, ellipsoidal equal volume orientation, it has got two components, right? That is the kind of cluster that it has created. So it has created only two clusters for us by default. So log likelihood is one measure of the effectiveness of the cluster. So the log likelihood, if I am comparing two clusters, the log, whichever cluster is having the highest log likelihood, that would be the most preferred cluster for me. And similarly, I would also look at the BIC, which is the Bayesian information criteria. The lesser the value, the goodness of fit goes for that particular cluster. So here the cluster has given me an algorithm saying there are two clusters, 247 elements go into one cluster, 53 elements go into the second cluster. It has by default, it has given only two clusters. But if I really want to see, compare the same, the 4 cluster solution itself, I'll give the same data but set G equal to 4. G equal to 4 is the number of clusters that I typically want. So this time, right, or probably I could have taken a different one altogether, right? Anyhow, we have seen here the BIC we got as minus 10,619 and the log likelihood was this much. So now we'll look at this G equal to 4 solution, right? I can now very well take the same summary. So this time it has given the classification of 4 clusters where it has taken the log likelihood is minus 5325. It is lesser than this case. So obviously compared to this solution is much better when I go with a log likelihood, because I could see that the log likelihood is higher for this particular function itself because it's a negative value. Similarly, when I look at the BIC, here it is minus 11,000. Here it is minus 10,000. Now, let me tell you one small correction here. BIC, and if I look at it as a regular BIC, right, the lower must be the better. But what mclust package typically computes, mclust function when it computes the BIC, it takes the negative of the BIC. Means when I actually do the BIC by regular mechanism, this comes out as 10,690 and this comes out as 11,011. Then I don't get the negative value, which means the BIC is lesser in this case. So wherever the BIC is lesser, that I would prefer. But when I am using the BIC from the mclust package, mclust function, what it reports as under this BIC heading is minus BIC. Right? BIC, whatever is there as a regular BIC, it gives me the negative value of that, which means just like the log likelihood, wherever this value is higher, I would prefer that model. So in this case, minus 10,619 is higher than minus 11,000, and that too I got a difference of close to 400 here. So the difference of BIC by that much extent is a clear-cut indication that there is a significant difference between these two cluster solutions. And the first solution that we have got, where there are only two clusters, is much more an effective solution compared to the second one. So either I can use the log likelihood function and compare the clusters. Wherever the higher the log likelihood I am getting, the better is that particular cluster solution. Or from the same mclust, if I am using the BIC also, the higher is the BIC, the better is the solution for me. But in real world, when I am using BIC, the lower it is, the better it is. But let me tell you, the mclust function here in the mclust package, whatever the BIC that it reports here is a pure negative of the actual BIC that is computed. So instead of taking the lower value, we will take the higher value and call it as a better thing. So basically look at the difference, right? Any difference which is 0 to 2, 2 to 6, 6 to 10, any difference that is greater than 10 in the BIC, I can say that the strength of the evidence is much stronger. I can very clearly say that one model is better than the other. And in this case, we have got a difference of close to 400. So there is no reason why I should not believe that the model which has given two clusters is much more effective compared to a model where we have forcibly gone for 4 clusters. So that's one more understanding that we are going with when we are doing the model based clustering. Right, so even here also we can do the same thing. Once the clusters are created, whether it is 2 clusters or 4 clusters, whatever it is, right, you could typically look at each of the clusters. So say customer mclust, right, customer mclust, this is what it is giving. Now you could clearly see what you really want. You really want the cluster memberships, right? So you can even go with the cluster memberships of each one of them. So either so you can simply call it as class. So basically, if you look at the you will get what function you need to use. Right, when I gone with this class, I could see here that I should use something called, okay, there are 15 call data. Where are the clusters being given? Okay, classification, dollar classification is giving me the clusters. right? So this is where I can say I can use aggregate, wherein I am saying this tilde. I'll take cluster, sorry, customer underscore mclust. So that's the name of my model. Dollar classification. So that's the kind of grouping I wanted. The data is customer, and I am looking at the mean. So I'll get my cluster means here. Here also I could see cluster 2 is having very average engage. Gender wise, again it looks more or less uniformly distributed. Cluster 2 again looks like low income group. More or less these are matching. Cluster 1 and cluster 4 are looking more like more number of kids. Cluster 3 is having lesser number of kids. So cluster 1 is looking majority of the home owners. Cluster 3 is again looking like not all those who have not subscribed to the product. So this is how the grouping of the customers is typically coming out. Again, I can very well go with my cluster plot kind of a solution to see if there is some kind of an improvement. So I'll do my customer, then I can take the classification. So I'll say customer dollar $m classification, and I can set color equal to true and labels equal to 4 to just to see what is the improvisation in the clusters. Here also this is how the clusters are coming out. The cluster solution is not getting quite heavily differentiated in any of the counts, even in this kind of a solution. I could see the cluster 2 again slightly differentiating itself here. Cluster 1 is more or less a subset, but if I go with a 2 cluster solution, let me see how it has come. Right, let me go with the 2 cluster solution itself. Instead of 4, let me go with the 2 cluster solution. Right, so this is my M cluster. Let me just use the aggregate class plot. I'm looking at customer, right? The labels, let me set it as 2. So even if I'm going with the 2 cluster solution, I'm not looking at anything, I'm not getting anything that stringently different across the clusters. Right, even if I do an aggregate, even if I'm looking at aggregate function across the clusters, it doesn't look that gracefully different across the clusters. They are more or less overlapping quite heavily. So in some cases my identification of the clusters may not be that great. So this is where we have to be very careful in terms of making some kind of conclusions based on our clusters, right? So the ultimate value that we are getting through the clustering solution is purely based on our strategy, the models that we are finally evaluating, and to what extent they represent the business solution for us. Now, on the similar lines, I'm moving towards understanding the latent class analysis. Right? You can probably try it out. POLCA is the name of the method, and the package name also is POLCA because LCA stands for latent class analysis. So I'm looking at polytomous, right? PO is nothing but polytomous. Polytomous means actually categorical. So we have already said that all the data here needs to be categorical in nature only. So polytomous latent class analysis is the name of this clustering algorithm. So that is where we have a function called POLCA, right? And here also, just like any other model based clustering, we are talking of the differences are attributable to the unobserved groups. So we have to really extract what those groups are. But this method, it typically assumes everything as categorical only. Now this is where we have to convert all our quantitative variables into categorical, right? We can very well convert all of them into categorical kind of variables. So probably this is where I can talk of, I can use my original customer data, right? Customer underscore cat, customer under. So it requires using only categorical variables. So this is where I can create my customer underscore cat. I'll take it as my customer data as it is. Right now, if I look at my customer underscore cat, which is my categorical variable, there are some numbers. So this is where I can very well convert customer underscore cat dollar age. Now I have to convert it into a category. So this is where I can use if else function, right? Just for quick understanding, either I can convert all of them into categories by putting some kind of rule. So I'll first have to convert them into a factor. So that's where I'll say factor of if else. I'll take this particular value, customer category age is less than mean of customer category age. I'll call it as category 1, otherwise I'll call it as category 2. So this is what I'm calling. So this is how I computed the category age. The same logic I can go with income as well. I'll convert that. So probably I can convert into n number of categories, but just for simplicity, I'm taking only 2 categories where I have simply broken out based on the mean values. Right, I have simply taken the mean. So I am taking the income. So I have done the categorization for the income as well. And same way, probably I can directly convert the kids without doing this kind of stuff. I can simply convert the factor of customer. So this I'll call it as kids. Directly I'll convert that into a factor itself. I don't need to do any other work. I'll directly convert it into a factor. So these are the categorizations that I have got. So now again, now if I look at the structure of customer underscore cat, so here I am getting everything with respect to factors itself. All of them are factors now. So this is where I can take, right, I can take it with respect to my clusters now. But when I have to do my clusters, so I can model all the dependent variables with respect to the model intercept. This is what I have to do now. I have to model all the dependent variables with respect to my intercepts. Now this is where I say customer underscore, right, customer underscore clusters, whatever PO clusters. So I'm taking with this particular customer data, with the categorical customer data that I had, all the customer data being categorical in nature, I'm trying to do a binding of all my variables, right? I am trying to do a binding of all my variables and I am trying to bind it with the intercept, which is 1. So I'll bind all my variables age, then gender. I'll bind all the variables. income. I'll do a C binding of all of them. So which is what? Otherwise I can do a direct C bind. Right? I can do a C bind. So let me see customer underscore cat1. Let me do a C bind directly of customer underscore cat and 1. So this is what I am getting customer. So I can very well now start doing the package. I can install my package now. The package I would like to install is polytomous latent class analysis. So POLCA is the name of the package that I am installing right now. And I will load that package POLCA, right? And now even this package goes with a seed. So let me go with a set seed of 100 and I will use POLCA function now. So I'll use a POLCA function wherein I can now go ahead. So I'll say customer underscore POLCA. I can very well engage this function where I'll take a POLCA function wherein I am taking the C bind. So I have taken the C bind, so I am calling it as customer category 1 where I have binded it with respect to the intersect. The data that I am taking is the customer underscore category. So I have taken the data as customer underscore category and I have to specify how many clusters I want. Let's say I wanted 3 clusters or 4 clusters to be consistent with the others. So object 1 is not found. Okay, so this is where I have to do a C bind. I think the customer character 1 has something wrong. So I have bounded the C bind of this entire categories tilde 1. Now let me see if I am able to get to that. Okay, so basically otherwise let me do another way customer underscore category 1. Let me simply say with customer underscore cat. I want to do a C bind where I am considering age, I am considering gender, I am considering income, kids, own home and subscribe along with segment. What is the definition of the segment? Capital S, right? Capital S segment. Right, I am even capturing segment and for this I am doing a tilde 1 and this let me put it here. Let me check what is coming out as customer underscore cat 1. So it is doing a C binding of all this. Okay, the variables might have got lost here. So you could do this kind of a function and once this function is there you can very well execute the POLCA function on the top of it. So this POLCA will again break down your data in terms of the clusters and once the clusters are created even when you are using your POLCA function you can very well look at the BIC of the models, you can do a quick summary, you can do a cluster plot, all of them and do a comparison of the models as well. So this process is the same whatever is the method that you are typically engaging. Once you know the clusters that are created, a few things that we have to be careful of. In some clustering solutions we have done a set seed. So depending on the random number that we are selecting as a part of the seed, our solutions also slightly change. which means it's always better that I run the models on different random number seeds, compare the results. And not obvious how to match one cluster solution to another. See, now I have got one cluster solution using the H class. I have got another cluster solution using the M cluster. I have got another cluster solution using k-means cluster. So we have different kinds of solutions which have given the results based on each of the clustering algorithm. And even if I know how to match each of the clusters, because the cluster 1 in the first solution may be same as cluster 2 in the second solution, because the names of the clusters have no meanings here. So the which group is to be called as cluster 1 there and which group as a cluster 1 here, we don't have any kind of a consensus. And even if we are coming out to some kind of a consensus on mapping it in the groups, we don't know what is the kind of an agreement rate. Okay, to what extent the matching should happen. Is it 90%, 95%, 99% or 5%? What is the kind of an agreement rate to say that these two clusters are more or less similar? Now this is where we are trying to use the map class function from the mclust package. So the map class function from the mclust package, it typically compares the two models that we have given, right? You can very well give the different models as your inputs. So whatever the models that you have predicted either through k-means cluster or any of them, where the matching can quite comfortably be done based on them. So you can give the clusters as an input. So you can give the predicted class as a part of the clusters, whatever the grouping that each of the solutions is giving, you can give as an input to the map class. And at the same time, you can use another function called adjusted rand index. So it talks about the degree of agreement. So if at all it has given all the observations to the largest group versus the cluster solution, it sees by how much extent your degree of allocation is much above than a random allocation to the groups, which is more similar to that of your R correlation value that you are getting. So the more and more you are getting the correlation value, the better is this particular cluster solution compared to that of a very random kind of allocation, all of them to the largest group. So that is how the cluster solutions can be compared, and based on that you can really make out which cluster, which classification of the clusters is much appropriate for your data. But let me tell you, all these are one side of the story. The other side is primarily where you can get your business results differentiated across the clusters. So these are the various things that we have looked up as a part of our session. If you have any further queries regarding this, you can very well get in touch with me by giving me a call on the number that I have given below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.